friends, welcome to this fifth lecture on calculus of variations. So we know that what we are doing is we are trying to find out the maxima and minima of functionals. So in this video, what we will try to do is we'll try to find out a necessary condition for obtaining maxima and minima of functionals. Actually, we will not reach there today. Like we will not be able to obtain this necessary condition today because we have to do a long work, but we are moving into that direction. What we are trying to do is we are trying to find out a necessary condition for obtaining a maxima and minima of a functional. uh, as we are more comfortable with functions, so we'll try to have an analogy between this functional and function thing so that we have more clear concepts. You already probably you will be knowing that excuse me, you'll be knowing that we know that if I have a function f of x, then the necessary condition for it has to have a maxima or minima at certain point is that the derivative of the function should be 0 at that point. Okay, you all know this thing. For example, if I have this function like this, then you can see that actually this point x naught is, all I'm talking about is local minima and maxima things. So you know that this x1 is a point of maxima. What do you mean by point of maxima? It means that there exists a neighborhood of x. Okay, x1 is a point of maxima. It means that there exists a neighborhood of x1 such that fx minus f of x1, you know can you see that because f of x1 is higher than fx for this neighborhood, all the x in this neighborhood, so we have that this thing is negative. Okay, this is negative or equal to 0 if x is equal to x1. So for the point of maxima, we know that like this thing should be true, that we should be able to find out a neighborhood of x1 such that in that neighborhood this variation in the function should be negative. And similarly you can see that x2 is a point of minima. It means that there exists a neighborhood of x2 such that f of x minus f of x2 is greater than equal to 0 for all x in that neighborhood. So and how this condition like comes, basically what we do is we look at this, if we are trying to solve the problem of maxima and minima, we are trying to find out all those values of x at which there can be possible maxima and minima. What we do is we look at this variation of f. Okay, at certain point, suppose this is f of x plus h minus f of x. So you are increasing or decreasing your x and you are subtracting that from f of x, and you know that if f is differentiable, then this is actually f of x times h, right? This thing is called variation. This is called variation or differential of f of the function at the point x, and obviously this is a function of h also. So basically, okay, let me tell you how this condition arrives, that f dash x is equal to 0 at the point of maxima. Now suppose you have some point x naught, not x naught, this point x1. We have this point x1 as a point of maxima. So it means that I know that this variation, there exists some neighborhood where this variation has to be negative. Okay, now if you are here, what is your h? H is actually uh, h is actually x minus, in this case x minus x1. Okay, h is x minus x1. So if you are on the right side of the neighborhood, so your x minus h is x minus x1 is positive. Okay, now you are saying that this is negative, this is positive, so it means that this has to be negative. This is negative, this is positive on the right hand side, so it means that this has to be negative. But on the left hand side, you have this x minus x1 thing. On the left hand side you have this x minus x1 thing like negative, because x is less than x1. So on the right hand side you have this thing negative, this thing negative, so it has to be positive. So what you are trying to say is, you are saying that the left derivative is negative, the right derivative is positive, but if your your function is differentiable at the point x1, so there has to be a unique derivative, right? So it means that your f dash x has to be 0, right? So this is your necessary condition. Necessary means that at least this condition should be satisfied. Like this will give you some values, x is equal to x1, x2 and xn. Okay, out of these n values, some points can be points of maxima, some points can be points of minima, and some points will be like this. Can you see this the curve is turning like this here. You will also get the derivative is 0 here, but that is not a point of minima, either minima or maxima. That is called the point of inflection. So this is a necessary condition. So can you see what you are trying to do is, you were looking at this variation and then you obtained a condition on the derivative. So basically you will look at the variation to find out a necessary condition for your function to have a maxima or minima at certain point. So similarly we'll try to find out what is this variation in case of functionals. Okay, so this was the analogy that in when we had a simple function of one variable, what we did was we tried to look at the variation, and we know that for the point of maxima or minima, that variation has to be, for maxima it has to be negative and for minima it has to be positive. And keeping that concept in mind, we obtained a condition on derivative of the function. So now let's try to find out the this variation of a functional. Okay, what is the variation of a functional? Let's do that. Okay, we are looking at variation of a functional. For that, suppose I have this functional j of y. Okay, y I am taking from some normed linear space. In the last video we have seen what is a normed linear space. So I have this functional. Basically this functional is from this normed linear space y to R. Okay, what it is doing is it is taking an element y from this these are functions to R, right? So, and what I want to know is, suppose there is an increment in y. Okay, I want to look at this is a variation, right? This h will again a function. This is a function, increment function. Okay, so I want to look at this thing. What is this thing exactly, right? For that I need certain definitions, so I'll define that first. The first thing is a continuous linear functional. Continuous linear functional. What is this? Functional, we know, it is a function from a normed linear space. Functional, suppose I have this functional. You can denote it with anything. Suppose I am denoting it with phi. I have a functional phi from a normed linear space V to R. This is my functional. Say that this is a linear functional. It is said to be linear if that phi of h1 plus h2 is equal to phi of h1 plus phi of h2 for all h1 and h2 in V. Okay, so it means that if I take any two elements of this normed linear space h1 and h2, this is the plus operation. You know that normed linear space is equipped with the plus operation, so this is that operation, plus operation. So what I should get is, like, I know that phi of h1 is a real number and phi of h2 is a real number, so this is simple addition of real numbers. So I should have this condition, the first condition. The second is, there is another operation dot in the normed linear space where alpha is a real number and h is an element from V. So what I should get is, I should get it like this. This should be true for all h in V and for all alpha in R. If these two conditions are satisfied, then we say that this functional is linear. Okay. Now, plus if it is a continuous functional, then it is a continuous linear functional. So now let's see what's the meaning of continuous in case of functionals. It's the same meaning we have in case of functions. So suppose I will say that this is the meaning of continuity of functionals. Okay. Continuity of functionals. I'll say that phi is continuous at some point y in v, okay, y not in v, if this phi of y tends to phi of y naught, like it comes closer to phi of y naught as y comes closer to y naught. Now, this is a real number, this is a real number, so you know the meaning of closeness. Now this is an element of V, this is an element of V which is a normed linear space, and I already told you that in normed linear space, what is the meaning of closeness? It means that the norm of y minus y naught should tend to 0. So what all I am saying is that I'll say that phi is a continuous function at the point y naught. Y naught is a point in V. It can be a function, it can be a vector, anything. If this norm modulus of phi of y minus phi of y naught, these are real numbers, so their subtraction is a real number, so I can definitely take the mod. It should go to 0 as this norm y minus y naught, this norm of y minus y naught is going to 0. Okay, more formally we can write that given an epsilon, there must exist a function delta, there must exist delta which will be actually a function of epsilon such that phi of y minus phi of, I'm sorry, it should be mod not norm, phi of y minus phi of y naught mod is less than epsilon for all y minus y naught norm less than delta. So basically what I am saying is I should be able to find out a neighborhood of y naught. Okay, how that neighborhood is defined? All those functions which are having norm close to the norm of y naught. So basically I should find a neighborhood of y naught. Okay, in like the neighborhood will contain the functions, and for all those functions this norm, that phi of y minus phi of y naught, this modulus value should be less than epsilon. This is the meaning of continuity in case of functionals. So basically if we have a functional which is linear means these conditions are satisfied, these two conditions are satisfied, and moreover if it is continuous, then that is said to be a continuous linear functional. That will be a continuous linear functional. Now let us look at an example of continuous linear functional. Okay, in the last video we have seen this CAB. This was a normed linear space. What space this was? This was the space of all continuous functions on the interval, on the closed interval AB, right? And how the norm was defined? Norm of any function y in this space was defined as maximum of a less than equal to x less than is equal to b norm mod of y of x. This is how the norm was defined, right? So what I am defining a functional, and I'll show you that is actually a continuous linear functional. I'm defining this functional phi from CAB, this is your space, to R. How I'm defining like this: phi of h. What I'm doing is I'm fixing some x naught in R. This is some fixed real number. So what I'm doing is I'm taking any function h from this space to its value computed at that point, fixed point x naught. Okay. Now I claim that it is a linear functional, linear continuous functional. Okay. First of all, let's check this linearity thing. Can you check it? Yeah, it's very simple. Phi of h1 plus h2. What will be that? That will be h1 plus h2. This is an element of v. V is CAV here. Computed at x naught. and we know that this is equal to h1 computed at x naught plus h2 computed at x naught. What is this? This is phi at x1 plus phi at phi at h1 plus phi at h2. So I have that phi of h1 plus h2 is equal to phi at h1 plus phi at h2. So this is the first condition of linearity. Second is phi of alpha h. What is that? That will be alpha h times x naught. What will be that? That will be alpha h of x naught. Okay, so what is this? This is alpha phi of h. Okay, so this is I got that phi of alpha h is actually alpha times phi of h. So this is the second condition of linearity. So this functional is linear. Now let us see the continuity. It should be continuous for all elements in V actually. So let us take any y naught in the CAV. So what I'm looking at this y phi of y minus phi of y naught modulus. What is this? This is h of, I'm sorry, this is y of x naught minus y naught of x naught. Okay, this is a number, this is number. Now you can see that this is obviously less than is equal to maximum of y of x minus y naught of x. Okay, if I compute the value of yx minus y naught x at a particular x naught, then it has to be less than is equal to the maximum over all possible x. So now what is this? This is actually norm of, this is how the norm is defined. So this is norm of y minus y naught. Okay, this is the norm. So what I got is that modulus of phi of y minus phi of y naught is actually less than is equal to this norm. Okay, so clearly I have that this thing will go to 0 if this thing is going to 0. I have phi of y minus phi of y naught mod going to 0 as this norm. Okay, so it means that when they are coming closer, these two numbers are coming closer. So it means that y is continuous for all. I have taken any arbitrary y naught. Okay, so for all y in CAV. So this phi is continuous, linear, functional. Okay. Okay. Now let's move ahead towards our aim. What we were trying to do is, I have this functional j, okay, from some non-linear space V to R, and I am looking at this variation. I am looking at this variation. Okay. For a fixed y, this will be a function of h only. Okay, this thing will be a function of h only. Right. So I'll denote that with del j of h. Right. So this is actually a functional. So suppose this j were the functional from V to R, this del j will be some functional from V1 to R. What is V1? V1 is all possible, space of all possible increments. These are the increments, right? These are functions again. So all possible increments okay. So this is a functional from this space, this to R. This functional may not be a linear functional. Okay, functional. Okay, let me write it completely. This may not be a linear functional, but if j is such that I can write del j of h is equal to some phi of h plus some epsilon times norm of h with epsilon going to 0 as norm of h going to 0, if this is the case, okay, where this phi is linear functional. If I can do that, then this functional j is said to be differentiable at this fixed y. We had a fixed y, right? Differentiable at that fixed y. Okay, is that thing clear? And this thing is called differential of the functional, and phi of h is called differential of the functional, and we will denote it with del j of h. Okay, is that thing clear? I'll repeat it actually, this is very important. What we are doing is, we had this functional from V to R, V is some non-linear space, and I want to look at this increment. If I increase for a fixed y, if I am increasing this function y with some function h, then I want to look at this increment in j of y, right? So this will be something like, this will be for a fixed value of y, this will be the function of h. So basically h is a function, so this is a functional. So del j is a functional from some space v1 say to r, which may not be a linear functional. But if my j, my original functional, is such that I can actually write this del j, which is a functional, like this, phi of h plus epsilon times norm of h, where epsilon is going to 0 as norm of h is going to 0, and this phi is actually a linear functional, then we say that j is actually differentiable at this fixed y, and this phi of h is called the differential of the functional and denoted by del j h. So now first of all I'll so basically we got this thing, del of jh is equal to del j of h plus epsilon norm of h, where epsilon goes to 0 as norm of h goes to 0, and this is a linear functional. This you will get if your j is differentiable. Okay, if you are given that j is differentiable, this is what actually we are saying. If j is differentiable, it means that this thing is true, and this is called the differential. First thing I'll prove is that this differential of a functional is actually unique, maybe we'll prove it in next video. Okay, that differential of a functional is unique, and then after proving that this differential is unique, we will try to find out a condition of maxima and minima for this functional, and it will turn out that you will obtain a condition on this differential. Okay, do you remember we had this in case of functions? We have del of f of x is equal to f dash x into h, right? And we were trying to find out a condition of maxima and minima, and for that we were looking at this variation, and we obtained a condition on this derivative. Okay, similarly here we have this variation. When we will try to find out a condition, a necessary condition for the existence of maxima and minima, it will turn out that we will find a condition on this differential. So it's important to study what this differential is. That we will do in next video. Thank you.